We are going to continue now with Kalle Ylä-Jarkko, and I will let Kalle to present himself. But the next two speakers are from our AI&ML team, and the two gentlemen are working with acquired companies in our portfolio. So they are working in the product development and R&D in the background with the companies whose solutions we are actually selling and promoting in Elisa industry. So the supply chain management solutions, the operations management, the MES solutions. So these companies are group companies, as we call them. They work together with us on product development. And now Kalle is going to present a real life case, and it's very interesting, at least in my opinion, so I hope you will enjoy. So Kalle, please go ahead. Thank you.
Yeah, so hello. My name is Kalle Ylä-Jarkko. Maybe I can say a few words about my background. So my background is not in computer science or AI machine learning. My background is in lasers. I'm a laser scientist. So I was, for example, a co-founder of a laser company, which is still working in Tampere, making high-power fiber lasers. And kind of my interest to machine learning came from that technology development, first developing products and then how to manufacture these products. What sort of things do you need to measure to get the manufacturing flow going? And then kind of finding out the problems that it is easy for humans to understand if there's one variable that causes the problem. Two variables, then it starts to be that only about 5% people can deal with that. But if three variables are interacting with each other, that starts to be impossible. So kind of my passion arose from this for machine learning was to find out these mathematical methods that you can nowadays implement, find code in the internet and start implementing and finding solutions to your problems by using clever methods. And especially encountering these situations where you have many variables interacting with each other. So here's the agenda of my talk. At Elisa, I develop machine learning algorithms for semiconductor industry and also into some other industries like battery manufacturing. And I'd like to start first with before we go into the use cases, I'd like to describe some of the new things I have found in generative AI that I think will revolutionize how AI will be used in manufacturing. So there has been an explosion in usage of generative AI in industry. This is a McKinsey survey where they surveyed that actually 30% of the organizations are already using generative AI tools regularly in one of their business functions. But surprisingly, in manufacturing area, usage of generative AI is lagging very much behind. And why is that? There's also this industrial robot paradox, and I think this is linked to why, for example, AI is not that much used in the manufacturing area, is that in manufacturing environments, there's typically a lot of dynamics, and the data is scarce, compared to internet where you have a lot of data and you can generalize things. But for industry, it's difficult to generalize things. So robots need to be adaptable. And also the communication with the humans has to be solved. If that's not solved, then the robots will be only used in very repetitive tasks. And there's a big motivation of using robots in the industry because the cost gap is huge. Additionally, there starts to be a shortage of skilled workers in industry. In next year, it has been estimated that in US there will be shortage of 400,000 welders. And at the same time also the workforce is aging in many industries. For example, in semiconductor industry, the average age today starts to be close to 50 years. And that's compared to then these tech companies where typical average age is around 30. And it is very difficult for semiconductor companies to attract young talents. They don't want to work there. So what to do? So I was looking into this, and I was looking for that. Can there be ways that this paradox will change? And I came across a couple of topics. One is called rapid adaptive AI, and I will show some videos related to this. I think every one of you, or many of you, have seen Boston Dynamics videos of walking robots. Yes, but those robots are something that have been pre-programmed to walk. They are given a script, instructions, how they should walk in beforehand defined territories. But these robots, based on rapid adaptive AI, have learned to walk. So they can modify the way they interact with the surrounding, improvise what should they do so that they don't fall down. So the motivation of me showing this video is to show that, okay, how these robots can, when they encounter situation, by the way, in the video the robot is blind, but how it can react to the changing situations rapidly and fast, and improvising what it should do. So these models, they have two models, or these robots have two models. One which is telling them in a generalized model how to walk. The other one is looking at the surroundings and telling that, okay, if they are raising foot and it doesn't raise 5 centimeters, it raises only 3 centimeters, what to do? Or where are we? We are probably in the soft environment, and then rapidly changing the things. So can this same thing be implemented in some other way? For example, in picking unsorted objects. So here's a blind robot hand using rapid AI. It is basically reacting to how it feels, or how the object feels in its hand. And you can see that it can move very different shapes of objects without seeing those at all. Okay, then one recent also advancement is these visual language action-based models. So basically the idea there is to interact the sensory system to language models. So you can feed in images and text, and the response is an action. So basically the robot you can give it a task, and then based on the visual, the robot looking from the images, it can basically react and change the movements into the direction so that the task is fulfilled. So this is a Google DeepMind work. But recently Tesla, for example, introduced this type of robot. For example, in this case, you are giving a task to pick up a strawberry and put it in the correct bowl. So the robot itself knows the surrounding. Okay, strawberries are in that bucket. I need to move it. It's not coded there. It basically has an understanding of the surrounding. So I think these are kind of the things that are revolutionizing the things in industry. And here's one kind of thing maybe showing that how far are we, or how close are we into implementation of this. This is from Global Foundries, which is one of the 5 biggest semiconductor manufacturers. And they had a problem that they have a lot of legacy devices, that it is very difficult for them to digitalize, that there has to be actually a man go and look at the sensors. So this is the solution they came up with.
Spot has an amazing athletic intelligence. It can literally go, up and down stairs, over all the terrains, out through snow, over different things, and get out of harm's way. Is how can we train Spot to know what it's looking at, and then to make decisions based off of that. Alerting somebody that this equipment is too hot, or maybe it's alerting to say, hey, there's something trending. We're predicting that this needs to be fixed before it goes out.
And go and collect that data.
Okay, so they created a system that basically is looking at the surroundings and reacting to if some equipment is going haywire, basically to reduce the scrap and basically avoid these dangerous things. So this prompted me to kind of raised this provocative question, are you ready for manufacturing, autonomous manufacturing? I'm not saying that it will happen this year or next year, but in 5 or 10 years, if there will be companies in your field coming with the solutions that the penetration of the robots is actually 30% compared to 1 or 2, are you ready for that? And what does it take? So I came across this survey from Roland Berger. It was titled Rise of Robots. So they listed topics that are hindering the penetration of robots or autonomous robots. So this is a list of these 6 topics that they came up with. So first one here is the picking up of an identification of unsorted items. So this relates to this robot hand I was showing. Adaptive control using machine learning advanced sensors. So it means that can the robot learn from the surrounding and react to what it sees and kind of the textual inputs. So I think that was already also covered, that there could be solutions for that. Safe human collaboration at economic speed. Okay, that's ChatGPT. Mobile automation of complex production tasks. I think this is something that is not yet covered, that how can the robots interact with each other and with the bunch of humans to kind of come up with a complicated task. And then, okay, next topic, advanced human-machine interface. So this means kind of an interface that citizens can code. So here's one interesting thing that few Stanford students did this year. So they have integrated AR glasses and generative AI, and they call it this as a charisma as service. So you put these AR glasses on and you start talking to a guy, for example, in a job interview. So this ChatGPT is listening what you are saying and then telling what you should say so that you appear as charismatic. But thinking of then yeah, I think Teemu was using those glasses. But okay, you can see where this is going. That okay, at the moment, ChatGPT can already generate code based on your textual information and test it. So where can this lead? That you can just tell that okay, do me this piece of code, and so that I can start using it. Okay, then this mobile automation and inspection and repair, okay, that was related to these global foundries. So many of the things, these kind of obstacles are relieved a little bit, or in few years will be relieved more. So I personally see that, okay, that this is a kind of progress that cannot be avoided. Okay, so how to jump into the AI train? So how to start building an AI case? Everything starts with the problem statement, as typically when you start with the project. Clear definition of the problem. Are you trying to improve yield, reduce scrap rate? Or do you want to do something related to predictive maintenance or resource allocation? Or what is your target? Is the problem you are having, is it persistent or only occurring once in a while? If it's persistent, AI can definitely help you because you will get in new data, so you get sustained benefits from the AI. Assess your data situation. So this is very important because machine learning is basically has a enormous hunger for data. But what it means is that you don't only collect real-time measurement data. You also need to, and most importantly, you also need to collect context data. What is your process flow? Which process comes after which one? How you put your equipment IDs, recipe IDs, do you collect those also? Then make realistic plans. What is the time to implementation, time to value? What is the expected business value you want, and how realistically you can expect that this project will be run? And think especially that can you start with small scale pilot project where you can basically test out the feasibility and then go full scale. These are kind of learnings what we have actually gotten with our customers, that how to have actually successful project. But everything starts with good problem statement, and it has to be a real problem, not just that you have a bunch of data and put the AI to look for that, okay, can it find any anomalies? That's not going to work. But in the end, what you want, you also need to be able to measure the effects. But like Teemu said, you should also think that I think in implementation of AI that you need to go up to prescriptive stage, so that you are not just looking at analytics, but your aim is actually to implement these intelligent actions that improve your yield and reduce the scrap rate. And this is often forgotten in the projects. Okay, our approach, we don't want to reinvent the wheel. Veli-Matti said that, okay, Elisa has purchased some companies, so we have purchased this Camline company from Germany, which makes statistical process control softwares. So what is statistical process control? I think every process engineer is aware of this type of control chart concept. So statistical process control means that you define upper and lower control limits, and you are looking for a certain parameter, the value of a certain parameter. And as long as it is between the upper and lower control limit, then everything is okay. Process is in control. And this is the concept what we want to still use, because the UI is familiar, but we bring in the machine learning. And these SPC systems are good in a way that they already collect the data. And also you typically have a lot of context data related to that the process flow is also followed in the databases. So it's a very good basis for machine learning. But in today's smart manufacturing, a lot of data is in very difficult formats, like images or time series data. And these are very difficult to put on a control chart. You use typically summary statistics, and then you have a lot of information loss, which leads to bad decisions. Okay, so what does this information loss mean in practice? So now I go into semiconductor industry. It's one of those most complex industries or processes are in semiconductor industry. And the manufacturing of one wafer nowadays can take up to 3 months. And it consists of up to 400 process steps that you are stacking very thin layers, having very thin patterns on top of each other. And after 3 months, then you know whether your process was successful or not. And it relies on the fact that the machines produce very flat layers and with a kind of certain footprint of symmetries. So there's on the wafer you are creating some surface profiles you want to follow. So there is a process called wafer mapping that is used in semiconductor industry, that after certain process steps they measure the surface height profile in certain locations, avoiding basically touching the actual chips, but they are measuring it in between. And they are trying to look at the surface profiles. And process engineers, they have already kind of knowledge that certain product types have a certain critical profiles. But to my surprise, this information is not really used well in semiconductor industry. They typically rely on summary statistics. And here I'm showing measurement results from wafers, from surface profiles. So the top control chart is the mean value measured from these 17 sites, that what is the surface profile, and the lower value gives you the standard deviation, so how much the height varies across the wafer. And summary statistics would indicate here that the wafers are looking exactly the same. And all the wafers are bad wafers, because the standard deviation is above the upper control limit. So statistics would say that, okay, you should implement exactly same actions to fix these wafers. This is a polishing process where you're trying to make a flat wafer. So you are applying radial pressure on the wafer. And you can clearly see that all the three profiles are completely different. So if you would need to radially apply pressure, different pressures to different zones, you can see that all the three wafers would need to have a different kind of pressure profile to be fixed. And that's contradictory to what the summary statistics are saying. So this is the information loss and leads to bad decisions. So how to fix it? So we have created algorithms basically where we are extracting features from wafers that's insensitive to actual measurement locations or measurement points. But we are extracting geometrical features out of the wafer. Always the same amount of features. And there's one coefficient for each feature. And these features have a physical meaning. They are this type of patterns. So tilt from bottom to up. or this type of pattern, or then tilt in the other direction, or a dome-like shape. And we are summing up all of these shapes based on the coefficients, and that reconstructs the wafer profile. So into these 10 coefficients, we are packing the information what the whole wafer looks like. So then we can start comparing the wafers. And if you look at these feature vectors in coordinate space, if the coefficients are the same, that means that the wafer is the same, has the same shape, and they cluster in the same locations. So then you can start looking at that, okay, where do normally my good wafers cluster? In what area? And you can kind of start defining these normal operating ranges, and then implement anomaly detection, which has already some knowledge of what the wafer should looks like. So you can think of also corrective actions much more easier than just using summary statistics. And these can then be further put into SPC framework for further analysis. So in practice, how does it work? So basically, there are measurement results which are uploaded to line workspace, which is a statistical process control software. And then we have created machine learning engine which interacts with this software through API. So the training data and also the measurement data is sent to the machine learning engine, where we reconstruct the wafer profile, and then we have algorithms defining critical profiles. We are finding the match and whether the profile is looking bad. And then if it's looking bad, within the software we have an automated, basically digital loop that corrective actions can be implemented automatically. So to the operator, then this system will tell that, okay, if the profile is sombrero, what should the operator do? Or if it's this type of antisymmetric donut profile, what the operator needs to do in that case. So that's kind of the operating principle here of kind of our systems. So then to the practical use cases. So we have a customer. It's actually had this problem related to wafer maps. So they had the problem that after certain process steps, they were measuring the wafer profiles, but they are losing 15 degrees of liberty. So meaning that there's 70 measurement points, but you are coming up with two values, mean and standard deviation. So there's a huge information loss. And that leads basically to a fact that two wafers having the same standard summary statistic can look completely different. And then it further leads that once it gives wrong out of control signals, it means that you cannot find the root cause for the observed deviations. And 1 year they were estimating that in 95% of the cases, they could not find the real root cause for the observed deviation. So in 5% cases, they were only successful. And they are really working there.
And it's very expensive, right? So it takes 3 months to build a wafer.
Yeah, so it also then takes a lot of courage to say that, okay, we need to scrap this.
Yeah.
So that's kind of why I've seen yield values that, okay, 20% of the wafers can have actually only 50% of the yield of chips after 3 months of production. But okay, so what are we then doing with the customer? So we are implementing machine learning algorithms that can do utilize the whole 70 measurement points, so are more accurate in detecting anomalies. But anomaly detection alone is nothing. You always need to have, related to anomalies, always people expect that you also they need to know why. So the why comes from collecting all the historical data that is relating to the manufacturing of the wafer. So there's measurement data, sensor data, recipe IDs from the equipments, machine IDs, all different kind of information we are collecting into this type of big process history table, and then using multivariate discriminant analysis method, which are typically used in biology, for example. We are comparing two groups, this bad wafer against the recent good ones. What differentiates these two groups? And what differentiates them is the actual root cause of the problem. And that is given as a list kind of that what is the most likeliest cause. And that can be like 8 process steps before the actual measurement happened. This same thing of anomaly detection and integrated automated root cause analysis can be applied also in the battery manufacturing. Battery manufacturing is a also interesting case and similar to semiconductor industry, that it is very complex. There are hundreds of variables interacting with each other. And also what is interesting in the battery industry is that actually majority of the, or almost 40% of the costs are directly related to the manufacturing process. And there are only few process steps that actually surmount 2/3 of the costs. And I'm looking at here the lowest ones, the formation and aging. So in formation phase, that's the phase that you first time charge the battery. And that's the time when you determine what is the degradation rate of your battery. You formulate this type of insulating interface, what is called solid electrolyte interface, in between the electrode, anode, and the electrolyte. And the lithium battery degrades in a way that the lithium ions want to escape from the electrolyte to the anode. So this interface basically prevents the lithium ion from going there. But the problem here is that nobody knows exactly how this interface is formed. And in the mass production, you cannot measure how this interface is formed. You can only look at the cycling data, that when does the degradation rate happen. And this is a critical also interface because it relates to safety, that how does the battery heat up? Why does it fire up? Well, you have problems in your solid electrolyte interface. So it's a natural way to look at that. Okay, that's the point where you want to locate the anomalies. And that's exactly what we have been doing. Here's the signals, what is basically collected in that charge-discharge cycle. So you are applying first current to charge the battery, different steps of current. Here there's blue curve showing 3 different type of current values which are applied so that the battery is charged up to 100%, and then you draw the current out. So that's the time series data what we have, and that's what we want to use to look for the anomalies. We don't want to use the summary statistics. Here's on the left-hand side good battery that can last for 2,000 cycles of charge-discharge, and on the right-hand side the bad battery only can last 300 cycles. And you can see, for example, that the charge time starts to increase in the end when the battery really starts to degrade. But what we want to do is that we want to utilize the data only from the first few cycles, where you don't actually see anything from the summary statistics, and still detect and classify whether the battery will be bad or good. So utilizing this data, we can then classify the batteries into class B, class A. So class B has estimated remaining useful lifetime below 600 cycles. And then what we utilize is we collect the historical data and find out that what is the difference between this class A and B in this case. And that's the root cause, what has actually caused why this battery is failing. And all this data can be basically whatever. It can be numerical measurement data or just textual recipes or IDs, and we can include that in the analysis. And basically overall goal, I was showing this rapidly adaptive AI. Okay, this is kind of, I made up this title. It's not really rapidly adaptable AI, but that's at least the goal for me, that we don't just want to find root causes, because that's reacting too late. What's good part is here is that these same algorithms that can find the root cause can also predict. So what I want to do is to create this cycle that, okay, you can early enough predict that what is supposed to come. And then you can detect that, okay, did it come? And if there's a difference, you can then improve the system. That's the way you can have this continuous improvement in your AI-based system. And that's what our goal is. So why AI? Sustainability. That's the one thing for me. On the left-hand side, I'm showing a graph of CO2 emissions from semiconductor industry. TSMC is the largest semiconductor manufacturer, which is based in Taiwan. Intel, I think everyone knows. So currently, the CO2 emissions from semiconductor industry are higher than from the car industry. And you can see that the CO2 emissions from the Intel are increasing, even though 95% of the energy is produced is green. Water. It takes about 3,000 liters of water to produce one computer chip. And this is a picture from Taiwan from 2 years ago, from their water reservoir. And that was the time that they called in fleets of lorries to basically get water for TSMC. Well, then money, of course. There's in next 3 to 5 years in semiconductor industry alone, by implementing AI, one can get value of $38 billion. So, thank you.
Thank you so much, Kalle. Very interesting. Anybody has any questions now? Or would you like to? You can also have a chat afterwards with Kalle at 11 if you like. Okay. Snorre, please.
How would you, now the example were here with the semiconductor and the battery, but how do you kind of apply this then to other use cases in other industry verticals? And what are the learnings so far that you have made in?
Well, I think the learnings there were captured when I was describing how to start with the AI project. So successful projects, they relate to the fact that the problem is clearly defined, and it is a real problem. And there is a real need from the organization itself that this is a valuable problem to be solved. So that is especially for the case for that semiconductor. There are passionate people there in the, for example, manufacturing, but also passionate people in the upper levels. And because they see that is a big problem and it needs to be solved. I think that's the most critical part of starting this problem or solving. Then everything else then comes naturally.
I was wondering a little bit that what is the limit where you do automation and where starts the AI? You had a good slide in the end about analyzing. A lot of that was statistics.
Yes, and there are different levels what we can use. For example, in semiconductor industry, we need to give the results to the operators and to the engineers. And there are certain kind of limitations on what kind of information we can give to the operators, that they relatively clear the decisions. And if we find the root cause, then okay, it has to be 1 or 2 things that can happen. And that's kind of one thing what we are developing into our algorithms, that we can get more of this why question, what Teemu was describing. That. And then we need to have a clear distinction, okay, that whether it goes to the operator or to the engineer. And to the engineer also we need to give different tools. They don't have time to look at these, so the tools need to be very clear, very visual. So explainability of this algorithm is important. And that's also one of the basis what we use to choose the algorithms itself, that we can explain also what is happening.
So basically when decision comes into play.
Yes, yes, yes.
I was just going to ask if you could touch on how this is implemented and how you provide this to the customers.
Yeah, okay. I took those slides away because well, in semiconductor industry, first of all, what they want is implementation in the edge. So they need to have the hardware there. We can implement this in the private cloud. So we have basically made a machine learning engine, and then also we had developed the web UI using JavaScript. So basically to explain the results. But the discussion happens through the API, that the data flows in JSON format from the mesh system to ML engine. The data flows, the training data flows from there using this API. And then, but also what we have noticed in the industry is that because of the dynamics, we need to think about what kind of models we implement, because they need to be updated relatively regularly. So for example, in this semiconductor case, we are updating them after each sample so that it's reacting dynamically to the situation. So that gives you some kind of speed requirement also.
What's the samples time frame?
Time frame is that we need to give the answer for anomaly detection within 100 milliseconds. And then this root cause analysis, okay, it takes 1 or 2 seconds.
Okay, and then the retraining is fast as well then?
Retraining is within that time limit, yes. Yeah.
So you have some device on site for that?
Yes.
Okay, because of the latency for the...
Yeah, it doesn't go to it's edge.
I think
That's why.
you have to come and have lunch with us after this, and then you can discuss further. Like really, yeah.